spring potential energy and gravitational potential energy. Before that, we will need to understand again the work energy theorem. Work is delta K. This is work applied plus work non-conservative plus work conservative is equal to delta K. Now, if work non-conservative, if work non-conservative is 0 and delta K is 0 when change in velocity is 0. This is a very important thing. So you will have work applied plus work non-conservative is equal to 0. This will give me work applied is equal to work conservative minus of this. This is a very, very important relation. Work applied plus work conservative will be 0, and this gives me this expression. Now, work conservative, I told you in my earlier lecture, that is delta U, change in potential energy. Therefore, work applied is equal to, using this equation, we have delta U. So in one statement, we have work applied is minus work conservative is equal to delta U. And this is a very, very important equation, and you cannot forget this because we will be needing this equation in the chapter, in the third unit also. Now, the point is spring potential energy we are coming to. Spring potential energy. Spring potential energy. This is what I am coming to. Now, the point is, number one point, if Fa is constant, or Fa moves the spring very fast, then W applied is equal to Fa dot ds, and this is from 0 to x. This is Fa ds 0 to x, because it's constant, I'm taking it out, and this comes out to be Fax. You know how to do the integration of this. I've shown you a number of times. Now, number two is if Fa moves the spring very slowly and steadily. So now this is the important concept. Now F conservative is equal to, let me put vector sign, K x vector, which will be minus always x of I. Let me take the I cap direction. Let us take ds vector as dxi. Now Fa will be equal to minus Fc vector, and that will be minus Kx vector, and that will be equal to Kxi cap. So W applied is equal to Fa vector dot ds from 0 to x. Let me take it as x. So ds Fa is this. Fa is Kxi cap dot, and we know ds is here. That is dxi cap from 0 to x. This x is a variable x, and this is some value. So this is k, I dot I is 1, kx dx 0 to x. So this integration is k x square by 2. You have lower limit 0 and upper limit x. This comes out to be half k x square. Now see W conservative. W conservative is, you know, W conservative is this. Fc dot ds. Let me write it down. Wait. Let me write it down. Let me pull it down a little bit. Yes, here. And let me. This was for my WA. Now for WC. WC, that is conservative, I'm taking this is as minus kxi dot dxi 0 to x, as usual the concept. I dot I is 1, so this is minus kx dx 0 to x is equal to minus k x square by 2, lower limit, upper limit. So this is minus half k x square. Now, okay, you can see that WA is minus of WC. Now, according to this point, this very important point, we will see what is potential energy, spring potential energy. I can use, using this equation, minus WC is delta U. I can use any one of them. So delta U is WA. So WA is already half kx square, and let me say delta U. In delta U, let me take this as U final minus U initial, where U initial is 0 and U final is this. So this gives me U. My spring potential energy is quantified. It never changes. Kx square. This is K, small k. X square. If I use these two equations, this and this, and now if I use this one and again this one, wait a minute. I used this equation and this equation to get this answer. Now I will use this equation and this one. See, now WC will be also from here also you will get the same answer, because again using this is 0 and this very is U. So I'll take U equal to minus WC, and I've already calculated minus WC here. That is minus of minus half kx square. So this is half kx square. Whether I calculate from the conservative point of view or the non-conservative point of view, the thing comes out to be same. Now let us see about gravitational potential energy. That will also be quantified as it was here. See, this expression and this expression are same. They are quantified. Whether you quantified means whether you find the potential energy from the work done or from the conservative work, you will always get the same answer. Now, next. So, spring potential, and let me write down this line. Spring potential energy is quantified. Quantified. It doesn't change. Whether you now we will whether you find it from the applied part or you find it from the conservative part. Now it is the gravitational potential energy. Now again the same gravitational potential energy. Now here also, suppose number one, if Fa is constant, force applied is constant, or lifts the body very fast, or lifts or moves, rather I should say moves the body very fast, moves the body very fast, the body very fast, then this time we are going to use, say, very fast, then W applied is Fa ds. Now it will go from 0 to h. Let me say Fa dot ds. This is Fa is this will move out, ds removing the dot product. This will be Fa into h, the height obtained. Okay, now suppose I take it very slowly. Suppose Fa, suppose, just a minute. Suppose Fa, external applied force, moves the body very slowly, moves the body very slowly, then F gravitational would be, this is mg, this is mg minus mg j cap minus mg j cap minus mg j cap, this is the gravitational, and applied will be minus of fg, that is mg j cap, and ds will be dy j cap. We are moving in this direction. Now this is g. This is g. Wait a minute. Let me write it neatly. Wait. This is g. That is the gravity. This is conservative work basically. Conservative work. Now again come to this point. W applied is Fa dot ds 0 to h. You have Fa is this mg j cap dot dy j cap. You have 0 to h. You have j dot j is 1. So mg dy 0 to h. It is now after integration comes out to be mgh. Now work conservative. This is, now let me write it down. Wait. Now again you will see. Wait, yes. Work conservative, that is work done by gravitational forces, Fg dot ds 0 to h is equal to minus mg j cap dot dy j cap. Let me rewrite this properly. Yes, wait. dy this is a dot 0 to h. J dot j is 1 as per dot product. This is minus mg dy 0 to h. So this is minus mgh. Now though this sorry, see, this is negative of this. Now you see work applied minus work conservative is equal to delta u. Again we will take delta u as u initial final minus u initial. We will take the initial to be 0 and final to be capital U. We will get capital U as earlier. So u would be WA. Straight away you can write down the value, that is mgh. Now this u, finding u from this expression of minus wc, you just found out minus wc, put minus of minus mgh, you will again get mgh. Now see whether you found potential energy from the point of view of applied or point of view of conservative, you got the same answer. So gravitational potential energy is also quantified. It doesn't change whether you derive it yes, whether you derive it from the work applied force idea or the conservative force part. Now the point is this expression, mgh expression, is valid only if the body is within the certain part of the earth. If you go up in space, then this uh, this one this one will not work. This expression won't work. This expression that I gave you here, see this expression. Now we will have to redistribute ourselves. I mean, we have to redistribute means that we have to rearrange the whole thing, and then we have to find the gravitational potential energy from space, outer space. Now in that case, now I will write down the complete theory, and this was asked in one of these external exam in one of these years. I don't exactly remember, but I'm going to do it for you, and then we will see that question later on. Now let me draw a line here. This line, okay. Now we will see when body is above the surface of the earth. Now gravitational potential energy from infinity, from the infinity point of view, from bringing a body from infinity, from bringing a body from infinity. This was asked. This is not. This was asked in one of the external papers last year, whatever it was. Now let me write down the theory for you, and this has to be written completely, incompleteness. Let us consider this situation first. Now, before I consider anything, and I can continue, let me tell you, this is our x, y, and z axis. In this direction, it is I cap, j cap, and k cap. The Earth is something like a sphere, so we will take the radial vector. This is the radial vector, r vector, and in this direction it is r cap. In this direction it is r cap, and outward direction is positive. I have taken the outward direction here as positive. Now see, now, sorry, sorry. Now we have this mass, this at the origin, a mass we have got O. Now we have got this at A. Let me shift this picture somewhere down. Let me draw this figure and then I'll explain you the complete theory. Wait, let me draw it here. Let me draw it here. Now see, you have a mass m at the origin. Now this is your radius vector. We are no more in x, y, and z. We are using this radius vector concept now. This is the position A, and in gravitational force field it is. Now see, this is the point B. Let the radius vector be of this will be called RA, and let this be called RB. No problem about it. Now the path is something like this. Some path like this is going. See, the radial vector is in this direction. This is the direction of the radial vector. This is the tangent to the path. This is the tangent to the path. This is in the direction DL. I'll tell you what DL is all about and all this. Wait, let me redraw this whole thing again. Let me redraw this whole thing again. We bring it somewhere here. Yes. Now, now you have to do one thing. Write this DL. This is the DL vector. Now see, this is the dr vector, small dr. The angle between them is theta. This is the body is moved in this direction slowly. The gravitational force F of C. Now conservative force I am writing. FC vector is in this direction, and applied force is in this direction. Listen very carefully. This is the direction of the applied force. Let me see if I can enlarge this figure. Enlarge this figure. I can wait. Let me enlarge this figure a bit. Yes, yes. Now I hope you can see this thing clearly. Now FC is in this direction. FC is in this direction, and your FA is in this direction. DR is also in this direction. Now this is the R this the direction of FC is this, but the R vector, the point position vector of this point. Let us consider the position vector of this elementary particle. Not sorry, elementary particle, but test mass. Test mass we call M0. M0 is this radius vector R. This line, this big line. Okay. Now don't confuse this arrow with the arrow for this R vector. This arrow is for FC, conservative. It is directed towards O. And this is R vector is from O to outward. Fine. This is the applied force. Now see what to do. I'll write everything clearly for you so that you don't have any problem understanding this. First you have seen this, now you see this. The complete theory I'm writing down for you. Consider, consider, consider a a particle, particle of mass m, this mass m, this is the origin, this is O, the origin. Particle of mass m, mass m, mass m at the origin, at the origin, at the origin, O. This is that O. This is that O. Test mass m naught, test mass m naught. You have to write the theory exactly the way I'm writing. M naught is moved from point A to point B. Point B, wait, point B, point B under the influence of under the influence of influence influence of mass m. That means the m naught is moving under the gravitational effect of m. Now force on this test mass, force on the test mass, we call it the test mass. It's of unit something, unit kg or something, like test mass. It's just a test mass. Is the conservative force acting on it is, this is minus, you know this formula already, m naught upon r square r cap. Now this is in this direction. I'll show you in the figure. I'll show you in this figure. See, it is, here. You can see this figure that FC is directed towards this direction, towards the origin. It is directed towards the origin. FC is directed towards the origin. Therefore, this is a minus sign because R is R cap. The unit vector R cap is directed outward. That is from this side. It is in the direction of, in outward direction. Fine. Now the point is, in order to, this is the most important line, in order to stop the acceleration of m naught under the influence of gravity, the acceleration of m naught, acceleration 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 of m naught, an external force, an external force external force FA, that is applied force, is applied in the opposite direction. Applied in opposite direction. In opposite direction. The complete theory must be written, I'm telling you, to get the full marks. Direction FA equal to minus FC is equal to, now with minus, when I multiply this becomes m naught upon r square r cap. Now this is the thing at the point P. Let's see where the point P is. The point P is here. The point P. See, let me write with a different color. This point is called the point P. This point is called the point P. This point. Now you will see that, wait, yes, now in the opposite direction, right? We have written this at the point P. At the point P. At the point P. Now, which is at a distance, this point P is at a distance of r from the origin, origin, right, where the mass m naught is placed, where the mass m naught is placed, right? Now I may make you understand what is the thing, what I wrote. The thing is this: I have kept a mass m naught here, and the distance of this mass from this place is r vector. This r vector, you're seeing this r vector, this complete line, r vector. That's what it's saying from the position O. Now the gravitational intensity. See, I talked about force. Now let me talk about gravitational intensity in this. The gravitational, I'll explain you. The gravitational intensity at intensity, it's called E. It's to be represented EG, is nothing but FC upon m naught, and this is nothing but minus G m. Let me write it somewhere down. Wait, let me write it here. Space is less. Let me write it totally differently. Here, EG vector, gravitational intensity, is conservative force by m naught, and this is minus G m r square r cap, and this is can be written as minus EG r cap. This is EG. This quantity is EG. Now, what is gravitational intensity? Let us understand. Suppose you are standing here with a gun and you are firing bullets. You're firing bullets. Now, suppose someone who is here, he will be hit by the bullet. This is the place of your action, and someone who is here may not be hit by that bullet. So the intensity of the bullet is still here only in this circle. Similarly, if I put a mass here, the gravitational, this is somewhere till here, not here also. This is what I mean. I hope you understood the thing. Let me rub all this now. Now, see the work done. Now, the work done by gravity. Work done by gravity. The work done by gravity is, see, now listen very carefully. This expression is very, very important. WC initial to final is equal to initial to final positions. These are position, initial to final positions. Supposing, let me show you what I mean to say. Supposing my initial position is this, let me draw this. Let me draw this with some color. This is my initial place, and I'm going till here, this place, final place, this initial to final position, whatever. So now, see, I can keep that, no problem. Now, see, what we are going to do, we are going to use this. See, this is, as usual, the formula is with FC, conservative force, dot dl. Instead of now writing ds, I am writing dl. Only the changes of the variables, nothing else. Now this is m naught, initial to final, eg vector dot dl vector. Now eg is directed inward. See, now you will see one thing. eg, I have told you already, this is minus, yes, this is minus eg vector. I just found out here. You can see eg vector I found out here. You can see this eg vector is what? Minus eg r cap. Eg r cap. I'm using vectoral form of doing the things. It is always safer to use vectoral form because they don't, you get a very clear picture about the thing. Now you should always use vectors only. That is the point. M naught, you will write Eg, the scalar part, r cap dot dl. Now dl, see, what I'm going to do is that this dl, I'm going to do one thing. See, I'm going to convert this dl towards the dr. I'm going to resolve dl to dr. Basically, that's the point. So something, so dl cos, I'll write it as dl cos theta r cap. Do not see still now that the dot product is still there. Now dl cos theta will be now initial to final. Now see, now this is minus m naught. This is eg as it is, initial to final. This is your r cap. R dot r is now 1 as usual, and dl cos theta, when I resolve dl in the direction of dr, I get dr. Now eg dr I get. Eg dr, this is initial to final. Now eg, you know what is this. Now you see, let us see what eg is all about. Now see, eg is what all about, minus g m naught m. Eg was what? Eg was just taking the scalar value m by r square. Just put that value. Initial to final, 1 upon r square dr. Now you know this integration, how to do. I've taught all the integrations. Now still I'll help you. I will help you understand this once more because some of you didn't have physics in 11th and 12th. So g m naught m, you integrate, it's like this, r minus 2 dr. This is nothing but r minus 2 plus 1 upon minus 2 plus 1. So you will get minus 1 upon r because of this result here. R to the power 2 minus 2 plus 1 and minus 2 plus 1. This will give me r minus 1 minus 1, and this will give me minus 1 upon r. That's why. This is the reason. This is getting reason, initial to final. Now you will have minus into minus is plus, g m naught m. Then you have your, you put the, this is r final minus 1 upon r initial. This is what your work conservative came out to be. This is your work conservative come out from initial to final. Now I will find out work done by the applied force. I'll find the work done by applied force. See, work done by applied force I to F. What I'll do is that this time I have initial to final FA applied force dot DL. Only in place of DL, in place of DS, I'm writing DL. Now this is same as you can say what is FA? This is nothing but M naught E EGR, because why? You have seen this here. Just see this. Just see this. Just see this. You have seen this FA is this quantity. That means if EG is this quantity, then if I want to write, see, FC is M naught EG. Let me write it down for you. Wait, let me write it down. And it will be easier for you to understand this thing. In bracket, I'll write it. See, your FC was FC by M naught, vector was EG vector. So this gave you, FC vector came out to be M naught EG vector, right? Now FA vector is minus of FC vector this, and therefore minus M naught EG vector, right? Now if I want to, this is the way it is written. Yes, you get minus M naught EG vector. Now therefore this is minus, here you have minus this integration from initial to final. This, let me write this in bracket so that the things are clear. This part is clear, I hope now. EGR dot DL cos theta r cap. Now this is equal to, if you see so, this thing M naught, I think, yes, just a minute. FC vector, FA vector is minus, yes, minus M naught EG vector. Minus EG vector, not right now. Wait. I made one simple error here. Yes. And let this be still be DL. Let this still be DL. Let this still be DL. No problem. Now you have minus M naught, right? Initial to initial, this is M naught is here. Okay. Initial to final EG, let me convert this EG into this. This is minus EG r cap, right? And dot DL cos theta r cap, right? Now the same concept DL cos theta, I am resolving DL in the on R dr. That is, I am doing, see, your DL is in this direction, dr is in this direction, DL was in this direction. This is the theta. Now if you find this, if you want to find cos theta, this is the perpendicular. Cos theta is what? What is cos theta? dr upon dl. Therefore dl is equal to, therefore dl is dl cos theta. dl cos theta is equal to dr. I explained you now. You shouldn't have any confusion now with this. Now minus of this part and minus of this part will make it m naught initial to final EG dl cos theta is again dr. dl cos theta is dr, as I showed you here. dr r dot r is 1. Now if you have put the values of just the modulus value, and this is g m naught upon initial to final dr upon r square. Now same integration as I did in the earlier part. What you do is that I will do the integration here for you. G m naught initial to final r minus 2 dr. So this is g m naught. This is, wait a minute. Yes, wait a minute. This is m naught initial to final. Now, oh sorry, wait a minute. Let's do the integration using the formula r to the power of n dr is nothing but r n plus 1 upon n plus 1. Here n is minus 2, and this formula is valid for r not equal to minus 1. Now here it is minus 2, so it is valid. This formula is valid. So you will use minus 2 plus 1 upon minus 2 plus 1. What I did earlier also. and I'll put initial to final, upper and the lower limit. So what I'll get? Wait, I'll get minus g m m naught 1 upon, this is r minus 1, initial to final, which can be written as minus g m m naught 1 upon r initial to final, which can finally, now our work applied, comes out to be minus g m m naught r final, putting the final 1 upon this, the upper limit minus the lower limit. Now, can you see one thing? This expression is just the opposite of this expression, conservative one, this conservative one. Okay, I have to write initial to final. Now, see, you don't need not do all both the expression in the examination. I did it for your sake of understanding this concept. Now, the main part is something very interesting, which you will see right now. Now, you will see that I will give you the gravitational potential, because in that question they asked you about gravitational potential also and potential energy. There are two different concepts. Now, let me give you in one line. Now, later on, I will deal deeply in this in the third unit. Potential is V. You already know, you write potential in class 10th as V only. In your class 10th, you had general science. In physics, initial to final, m naught is equal to minus initial to final conservative m naught, and this is your change in potential energy upon m naught. V is the potential. Try to understand gravitational. Here it is gravitational potential. Here it is the gravitational potential. V is this V is gravitational potential, and that this U is nothing but gravitational potential energy. Just the one extra word, nothing more than that. Potential energy. That's it. Now, see one thing very interesting. You will see if I use delta V can be written as, we just found out. This is a very, very important expression. Wait. Let me mark it for you. Let me mark it for you. Can you see this? W initial came out to be something like minus of this quantity, right? And W applied came out to be plus of the quantity. This W applied and this is the plus of the quantity, EGDR. I'm talking about this. Let me rewrite these expressions. Let me rewrite these expressions for you once more. This expression came out to be minus of this part, this much part, you see. And this applied came out to be positive of that part. Did you see this? Can you see this difference? Now, let me read. Before I write del V, let me write down those two expressions so that, see, what did I write? What did I say? W initial to final applied, I wrote minus, applied, sorry, I wrote W applied, wait a minute, I wrote W applied, I wrote M naught EGDR. I wrote M naught EGDR. M naught, I wrote M naught, wait a minute, let me rub everything. Now, M naught EGDR. There is no vector, all are scalar now, from initial to final. Now, in place of W conservative, initial to final, I wrote minus M naught, initial to final, EGDR. I wrote, I hope no confusion here. Till here, no confusion, because you can see W conservative came out to be, this conservative came out to be minus, got the point? And this W applied, sorry, this W applied came out to be plus. I hope there is no confusion now. And EG is just the constant value. EG is this the constant value, this constant value EG. You don't have to go for the vector. This is the constant part. Only I'm not talking about any vector right now. Now the thing is this gravitational potential energy. Now things will be very easy for me. See, before that, let me tell you gravitational potential, just gravitational potential. You may write, compare this equation, see this equation. This is let me mark this equation properly for you. This is an expression you will be, sorry, just a minute. This expression you will again be using and making things very, very easy for you in electric fields. This whole equation. Let me rub this signs so that you don't get confused. This is the thing, expression for you with a negative sign here. Here is a negative sign. Wait a minute. Here is a negative sign. Here is a negative sign. Very important. This expression is the crux of the complete thing. Now, del V will be using that equation, using this equation. Either you use this one or I use this one. I will get del V equal to whichever I use. M naught initial to final EGDR. Now I need not calculate. I mean, if you want, I can calculate for you. Look, M naught EG is what? GM, and dr upon, now this is r square initial to final, so this is minus gm m naught, sorry, I have to write egdr, sorry, del v is upon m naught. This is m naught, this m naught cancels out because it is w. See this expression, see this expression, see this expression. This is del V is W applied upon M naught minus WC by M naught. And what I have written here, it is WA M naught. So I have to divide this WA by M naught. So M naught cancels out. I don't get this M naught here. Sorry. I don't get this M naught here. I get only this. Now I will do the integration. Integration is very simple. I've told you this. This is minus. This is plus. Wait a minute. Let me rub this also. So when I do the integration, I get this. When I do the integration, I get minus r from initial to final. And then what I get is del v comes out to be minus gm r final minus 1 upon r initial. This is the gravitational potential. Now we will talk about gravitational potential energy. We will talk about, see this expression again, see this expression again. Now here it is your gravitational potential energy. So gravitational potential energy will be equal to work applied. Compare this equation with this equation. So both will be same. So from this equation I'll get delta U is W applied this. That's right. Or if you want to write, you may write this is M naught EGDR. Again, you want to do some integration to have some more experience on integrations, you can do it. Especially I'm doing it for those people who do not have any idea of physics and maths in class 11th and 12th. Because in BCA, many people are here without maths and physics. DR, with this integration, what I get is, see, minus GM naught upon R, upon, wait a minute, just a minute, into 1 upon R final minus 1 upon R initial. This is what I get. Now, in bringing the point, the question that was asked in this externals of IPU, International University, was what would be the situation if I bring a body m naught from infinity to R. Now see, let me write it down. In bringing the body from infinity to R, that means R initial would be infinity and R final would be, say, some R. Say some R. So gravitational potential energy, gravitational, wait a minute. Gravitational potential energy, potential energy, that is, that is delta U. Let us say U initial is 0 because, let me tell you why, and U final is, let's say, U. Why? Let me tell you. See, this is your planet Earth. Here you have potential at infinity, this point at infinity, the initial potential is considered to be 0. And here we have some potential. That's the reason. That's why we take initial 0 and final this, in this case. So delta U, if you write, you have U minus 0 is equal to minus, you had what expression? You had minus gm m naught. Now you have r 1 upon r minus 1 upon infinity, and this 1 upon infinity is 0. So 1 upon infinity being 0, though it is, so u is minus g m naught by r, and this is always quantified. This is quantified. This gravitational energy is quantified. Whichever expression you want to uh, derive this, you will get the same value with this minus sign. So gravitational potential energy is quantified. See one thing. First, see whether the question they're asking is for within the earth or from outside the earth. If it's outside the earth, you need to use this, or if it's within the earth, then you can straight use this one. This expression, wait, this expression that I did. I hope you have understood the complete theory of all this. You may have to pause the video. Let me scroll it little slowly so that you can at least see things, and you can write down, stop the video, and then write down the complete theory. And whatever I've written in the site, please write them down. It will be very easy for you to revise before the exams. I hope you have now understood. Though you need not write this word, gravitational potential energy is quantified. This I told you just for your knowledge part, nothing else. It's not, they don't ask that much. If they ask, fine, you know it. It's okay.